So I'll talk about this artificial leaf and how it connects to solar energy. One of our focuses, though, has not been the generation of energy using solar. We feel that, and I'll show statistics, that silicon and other ways to generate solar are becoming very prominent. There are many ways to do it. And cost has been going down, especially with silicon, because China has made a huge investment in silicon. So they've built multi-billion-dollar plants now to produce silicon. And so the price, only 5 years ago in any economic modeling, the price of silicon was $4 per watt. And you can see now its average is under $1 per watt. It's because of this massive investment that China has made. So what we feel is the real problem with penetration of renewables, especially solar energy, has been the inability to store renewables. And this, I was involved with a company that's now gone to Lockheed Martin, so we did a lot of analyses in the last few years. And the storage market is probably one of the most attractive investment markets coming in the next 10 years. So you can see here, these are all different age companies and analysis. And you can see that the market for solar energy is just increasing dramatically. Some people estimating it to be almost a $500 billion market in the next 10 years. So this idea of how do you store solar energy is going to have a massive market drive, especially with what's going on in China with the production of silicon. So today's talk is going to talk about how to store solar energy in the form of fuels. You can also store it in the form of batteries, grid storage. We've done some of that, but Professor Giraud will be talking about that later today. So I'll talk about fuels. And the energy fuel that we've chosen is hydrogen, and that's based off of photosynthesis. So here, what I'm showing is, and this is what we remember about photosynthesis, is sunlight plus water plus CO2 makes oxygen in biomass, carbohydrate. And what people forget sometimes is all the solar energy is stored in the production of hydrogen and oxygen. And hydrogen in nature isn't stored as a gas, it's stored as NADPH. And that is where all the solar energy is stored. And you can see here in the splitting of water, that is 1.23 volts. The next reaction, taking hydrogen, CO2 to sugar or biomass, you only store an extra 0.01 volts in that reaction. So all the solar energy is stored up front in water splitting to make hydrogen. The biomass in sugar is an engineering problem. The plant couldn't deal with hydrogen, a gas, so it fixed hydrogen with CO2 in the dark. That's a dark reaction. Plants do that in the dark at night to make sugar, and that's a hydrogen storage mechanism. So I'll mention today, I'll talk about this first piece, how to split water to hydrogen and oxygen. And then at the end, I'll talk about how to combine hydrogen with carbon dioxide, in our case, to make a liquid fuel. So I'll deal with both parts of this. And the way photosynthesis works, the leaf, is, and I'm only going to worry about the function of photosynthesis, is sunlight comes into the plant, and then the plant can't manage photons. So what it immediately does is it sends in the photosynthetic membrane, it sends an electron in one direction in the membrane. That leaves a positive charge which goes in the opposite direction. And so you have charge that's moving, and moving charge is current. And what the leaf does, the only difference from what you're used to, current is usually in wires, the leaf does this without wires in a wireless current. And at that point, it stores the electron in a cofactor, an iron reductase, and it stores the positive charge in a cofactor, the oxygen evolving complex. And at that point, the leaf is a battery. It's stored charge, just like you would at a metal center in a battery. But that batteries have energy densities that are 100 times smaller than a fuel, and the plant knew that. So after taking 4 units of charge, it does it 4 times, it increases the redox level of the cofactors, so the battery gets 4 units of charge, and then it uses that charge in the cofactor to do catalysis and rearrange the bonds of water to make oxygen and hydrogen. And like I said, it doesn't make H2, it makes nature's form of H2, NADPH. And so understanding this sun-in wireless current and then catalysis to do hydrogen and oxygen, we wondered if functionally, so that's why I'm calling this artificial leaf, it's a functional form. Could we do the same thing, have sunlight come in to a material, get 4 units of charge, and then have 2 cofactors, catalysts, that store the electrons and holes and then act on water to make hydrogen and oxygen. So we wish to duplicate that process. And I have to mention that we took a little bit different approach than the conventional approach to do that process. So previously, there are things called photoelectrochemical cells, and a photoelectrochemical cell does just what I mentioned. It takes sunlight to make a current and then make hydrogen and oxygen. But most photoelectrochemical cells were designed such that the material that absorbs the light, and here there's 2 materials, so this would be called a tandem cell. That material which absorbs the light also does the catalysis. So there's lots of approaches since the 1970s. This is also known as a Gerischer cell or a solution photoelectrochemical cell. In these types of approaches, the semiconductor also does the chemistry. And that's different than photosynthesis. If you think back of what I was saying here, photosynthesis absorbs light and makes the wireless current and then does catalysis and cofactors separately from the light harvesting and circuit network. When you have this design, then you get these types of pictures where this is showing the energy of the chemistry you need to do. So this is making hydrogen and oxygen at 1.23 volts. But you have to make sure that the material has enough energy so that when I excite an electron from over here to over here, the conduction to valence band, you have to make sure that the conduction band conduction to valence band. You have to make sure that the conduction, you have enough oxidizing power, or be on this side of the line to make O2, and you have to have enough reducing power to make hydrogen. So in this type of approach, you have to make sure the band gap spans the chemistry you're doing. And that's a difficult thing to do because semiconductors, the property that makes something a good semiconductor makes it a very poor catalyst. Catalysts need to operate at 4 electron, 4 proton potentials and do intricate chemistry to couple the electron and proton, while the semiconductor likes to operate at a 1 electron process. So besides having this thermodynamic problem to contend with, you also have the problem of taking something that is a material for applied physics and trying to do chemistry with it. So we went to a design that was actually popularized by NREL called the Berry junction, where you take a photovoltaic material and put it between 2 conductors and then cover the conductors with your catalyst. And the advantage there is, as long as you have sufficient potential, because the semiconductor is between two conductors, it's called the Helmholtz layer, it immediately adjusts to the chemistry in solution. So you don't have to span any potentials. This effectively is whatever chemistry you're doing, as long as you have the potential, it will adjust to the chemistry. So that's the first simplifying feature. And then the second simplifying feature is you can optimize catalysis independently from the photovoltaic material. And in the catalyst that photosynthesis does, you need to worry about this issue of proton-coupled electron transfer. And what I'm showing here is just to take protons to hydrogen in acid at the normal hydrogen electrode. That's a 0-volt potential process. But if you don't couple electrons and protons properly, then to add an electron to a proton, you make H dot. That's 2.3 volts uphill. And then the next electron and proton you add is 2.3 volts downhill. So to run a 0-volt reaction, you're having to go over a 2.3 volt hill. And so you need to couple this electron and proton to try to minimize that energy barrier and do the most efficient catalysis. For water splitting, to make the other half of the reaction, this is the hydrogen piece, to make oxygen, you're actually storing 1.23 volts. So you have to minimally go 1.23 volts uphill or over a barrier. But again, if you're uncoupled, for instance, titanium oxide, the way titanium oxide, a semiconductor, splits water is it does it one hole at a time, and it actually makes OH dot, and that's a 3.2 volt barrier. So again, if you don't couple the electron to the proton, you end up confronting these large energy penalties. So many years ago, we spent a lot of time trying to figure out how to couple electrons and protons. And the way we did it is we made compounds where we could, because electrons are quantum mechanical, they're spread out, so they can travel over much longer distances than the proton. So what we did is we made compounds where we could start the electron, say, on that side of the room, and have it show up to that side of the room, but we started the proton very close to that side of the room so that when the electron and proton showed up, they would show up together. And that allowed us to begin timing electrons and protons and building kinetic models and ultimately developing the first theories for proton-coupled electron transfer. And this basically shows that the electron is quantum mechanical, so in terms of how fast it moves depends on its wave function overlap. The proton is Newtonian, it's classical, so it has a much smaller overlap at that distance and therefore becomes uncoupled. So in designing catalysts, you need to figure out how will you have short proton hops coupled to long electron transfer distances. And we, with all that knowledge, began developing compounds that look like this. These actually come from solution. So we put cobalt in aqueous solution, and when you oxidize cobalt 2+ to 3+ in the presence of phosphate, you'll have this material precipitate out on an electrode. So here's an electrode surface, and here's this material. It's heterogeneous material, but it's a molecular compound. And it has this picture of cobalts and oxygens. And actually, when we did this science, we actually went into the geology literature because the geochemists have worked out the solubility products and kinetics of formation of cobalt and different metal ions from aqueous solution in the presence of anions. So we literally used the geology literature to design these types of compounds. That compound looks a lot like the oxygen evolving complex. This is the stick line drawing of the oxygen evolving cofactor that splits water to O2. It has manganeses in a cube, and it has a dangling manganese with a calcium. If you take that cube and dimerize it and replace manganese with cobalt and rotate it by 45 degrees, you get that structure right there. So this structure here is fused cubanes, the cubanes that are found in the oxygen evolving complex. And this compound works a lot like the OEC. This self-assembles from solution using cobalt. The manganese OEC self-assembles from solution oxidizing manganese 2 to 3. It has the same cubane structural element. And these two properties, it turns out this oxidizes water with exactly the same mechanism or proton-electron inventory of the photosynthetic center. And this is self-healing. And because it's self-healing, you can use any type of environment or condition to do water splitting. So I'll quickly, and I'm going to do this very quickly, just explain, and this is too much chemistry, but I just want to give you a feeling of the type of experiments we've done, because this is at the heart of self-healing. So the way the cobalt forms, we've spent many years now working this out using electrochemistry, is you oxidize cobalt 2 to 3. So here's cobalt 2. It gets oxidized to cobalt 3 by a proton-coupled electron transfer. So let's just keep track. I oxidize 1 cobalt, so that's why there's only 1 cobalt in this rate law. This is the kinetic rate law for the formation of the material. It's inverse third order in protons. You see I have to lose a proton here. I have to lose a proton in the oxidation of cobalt 2 to 3. And I have to lose a proton finally after I oxidize the cobalt 2 to 3. This phosphate needs to leave before the cobalt can lay down onto the material. So if you do the calc, there's 3 protons. I have they're inverse third order. I have an inverse first order in phosphate. That's how you make this material. In the manganese system, it's a disproportionation. But again, we know all the numbers of protons, electrons, and electrolyte. In the water oxidation process of taking water to O2, here's the kinetic rate law. And it's a 1 electron, 1 proton process that delivers the active catalyst, which is then rate determining to make O2. And so now, just look at this right side. I have 2 different kinetic rate laws. I know how to make oxygen, and I know how to form the catalyst. And it all has to do with this proton-coupled ET, so the proton and electron transfer. And you can see here, at, let's say, pH 7, neutral water, at the potential to do water oxidation, I'm at 1.2 volts. And at that voltage, I have plenty of voltage or over voltage to form the catalyst. And the reason for that, and this is why we invested so much time in this process, is the formation is inverse third order. So it's a much steeper line. You can see this line's much steeper than the water oxidation. And so therefore, at any potential above or pH above 5, I always have enough potential to have the catalyst, if I lose cobalt in solution, to heal itself, to get reoxidized and lay back down on solution. In the case of manganese, because it's inverse fourth order, we can actually do water oxidation using an oxide at pH -1. We can run this out of concentrated nitric acid and do water oxidation with no loss of catalyst, because we're always having enough potential to heal this catalyst. So that is the piece that does water oxidation. If you're making O2, I told you we have a preference for silicon. You'll then be making oxygen in the presence of silicon. That will make SiO2. So you have to protect the silicon. We do it with fluorinated tin oxide now. And a single junction of silicon can only put out around 0.6 volts. Water splitting is 1.2 volts. So you need to have more than, that's not enough energy, so we had to put contacts on there because I'm going to have to put extra voltage in. And we did that, and you can see here, this is now the silicon electrode. When we do water oxidation, it occurs at around 1.2 volts, like I've been showing. But the difference here is now when I turn on sunlight, I'm going to generate an internal voltage of 0.6 volts. So now, whenever I turn on the sunlight, I don't have to drive the system with an external voltage as hard, because internally I'm generating 0.6 of a volt. And you can see the green line is water oxidation under sunlight. This is in the dark. And at any potential, I'm offset perfectly by 0.52 volts. That then tells you the thought experiment. If you put two together, I should get 0.5 volts plus 0.5 volts. That's 1 volt. So now I should oxidize water at around 0.23 volts, and that's what happens. So then, just continuing along this line of reasoning, if I were to put 3 junctions together, then I have enough potential to split water, and I don't need any external voltage, and I can just use the sun. And that's what we did here. We also need to make a hydrogen catalyst. So we took a triple junction silicon PV. We then put we then took a conducting layers, put the oxygen catalyst on one side and the hydrogen catalyst on another. The hydrogen catalyst we made is a nickel molybdenum zinc alloy. And you can see with the germanium amorphous silicon, that's the top layer, it's 400 nanometers. When you put germanium in there, germanium's bigger than silicon, it relaxes the lattice, that shifts the middle layer to 600 nanometers, and depending on how much germanium you dope in the bottom layer, we could dope a lot of germanium and we get 800 nanometers. When you take this curve, that matches pretty well the solar spectrum. And it's generating 1.76 volts. That's plenty of energy to do water splitting. So you can literally just take this wafer coated with the catalyst, just hold it up to the sun, and at the solar current density, you can generate H2 and O2. And that's what we call the artificial leaf. Now, and it does it 4 units at a time. So 4 units of photons gives 4 charges. They're stored in the catalyst, and then you split water. Recently, we made a little more complicated design. Amorphous silicon isn't made at industrial scale. Crystalline silicon is. So we made what's called a tunnel junction. This is a little bit more highly engineered, but it's crystalline silicon. With our catalyst, this is the IV, or the current voltage performance of the catalyst. Here's the PV. We're able to split water to make hydrogen and oxygen at an efficiency of 13% using crystalline silicon, commercial silicon. To end, I think I have 3 or 4 minutes. To end, I want to say that we're making hydrogen, so you need a fuel cell to burn it. And as I mentioned, nature doesn't use hydrogen. It finally fixes the hydrogen and makes biomass. So we were interested, could we take the hydrogen that we're making from the artificial leaf and make a liquid fuel out of it? And to do that, we went to biology, because in biology, making carbon-carbon bonds is very difficult in chemistry. What we're very good at is breaking bonds, but we're not good at stringing lots of carbons together. Biology is. And some of these fuel processes I'm talking about are 24 electron, 24 proton processes. And evolution has naturally adapted to multi-electron, multi-proton coupling. So I'm now showing a schematic of a leaf. Here's photosystem 1 and 2. That was where light comes in and makes the wireless current to make oxygen and hydrogen. We're now doing that with the artificial leaf. So I can lose that whole photosystem. You still have the Calvin cycle. Here's the hydrogen in the form of NADPH. It's fed into the Calvin cycle where you take CO2 and hydrogen and make biomass. So what we did is, in the last year and a half, we took a bacterium, and because of systems biology and knowledge of genomics now, we know if I put a certain gene in a material, I can get a certain function. So we took a bacterium called Ralstonia eutropha, and we took the genetic code to put a hydrogenase in place of photosystem 1 and 2. And what the hydrogenase does is it breathes in hydrogen and makes 2 protons and 2 electrons. which then from the other side of the hydrogenase goes to NADPH, which can feed into the Calvin cycle to make biomass. And the hydrogen, like I said, now comes from our artificial leaf. And that works beautifully. We're able to take this special form of Ralstonia, where we've done the systems biology, put the hydrogenase in the membrane. And what it's effectively allowing the bacteria to do is now breathe in hydrogen and use hydrogen as its nutrient to live. It then takes, we're not giving the sugar, usually to keep bacteria cultures, you have to feed it energy. So the energy is literally the hydrogen coming from the artificial leaf. It breathes it in, and we can make biomass directly inside this bacteria. But of course, with biomass, you still need to convert that to a fuel. And again, we've taken advantage of systems biology. And at this stage, in this Calvin cycle, you get to what's called acetyl-CoA. It's a precursor that with two genes, we had to use two genes to knock out the regular pathway to biomass. So those are genes. We took those genes out of the bacteria, and then we inserted four other genes, 1, 2, 3, 4. And what those 4 genes do from acetyl-CoA is they make isopropanol. So now what you're able to do is have hydrogen come in from the artificial leaf. These bacteria breathe the CO2 and hydrogen in, and we're able to make biomass at 2.3%. You have natural biomass is 1%, the fastest growing plants, so we're better than those plants. And we're at 1% now making isopropanol directly. I will tell you, while we were doing these studies, there was a mutated bacterium we found that would live forever in the presence of what are called reactive oxygen species. That allows us now to run the cycle even lower, and by the end of the year, we'll be hitting a light into isopropanol efficiency of 5%. So this is advancing rapidly. I just want to end. What I'm talking about here, we can do everything I said at large industrial scale. So we can take CO2 with Fischer-Tropsch to liquid fuels, but you need large plants to do this, large industrial plants. Everything I'm saying here, you can do at the bench or in the backyard. So it's this idea of going from a centralized energy system to what we've done with personal computing to a decentralized, personalized type of energy system. And I think for at least the students in the audience, that I believe will be the challenge for the next 100 years. Everything that we do in a very large centralized way, which is good for societies that have lots of money because they can build large plants, we're going to have to, for the poor of the world, which will be driving our energy demand, figure out how to do this in a distributed way cheaply for them. And the sorts of things I mentioned today about the artificial leaf, the hydrogen, and now the liquid fuel is one road to doing that, to help the poor get on equal footing with the rich in the world for using solar energy as their energy supply. So thank you. Do you want to have questions? Or?
Yes,
okay.
we have time for questions.
Some questions.
Comments. Want to start? On the back. Oh, pardon. Jean Salençon.
Yes, I wish to thank you for your very comprehensive lecture. And I have one question. I would have many, but I would choose only one. So as far as water splitting is concerned, how does your process compare with the classical one, would be electric water splitting, electricity being produced by classical photovoltaic cells, for instance, with high efficiency?
Yes. So the question is, there's two ways to do this. This is direct, sunlight to hydrogen and oxygen. Indirect is to take a solar panel and then wire it to an electrolyzer and then split it to hydrogen and oxygen. One good outgrowth of our study is we were able to make an electrolyzer with our catalysts and silicon and then compare it to this direct method. And what you find is there's practically no cost differential. They're very similar in cost. In the United States, by the way, it's promoted that direct should be much cheaper. But I'll tell you where you get hit. In the electrolyzer, you can do a thing called electrochemical compression. Every 60 millivolts, Nernst's law, you can up the pressure by a factor of 10. In the direct, you're going to have to do compression downstream. So what you make up on cost on one side, you start to take a penalty on another side. So in my opinion, the advantage of these two approaches will depend on the application you're using. The artificial leaf, which is working in water and phosphate, for instance, is very well adapted to interfacing with biology. While these electrolyzers tend to be run in concentrated base, and they're not adapted for biology. And so I really think when you start looking at the full market analysis, you'll find that you'll have cost benefits with one approach versus another approach. But in general, I would say they're not that different at a very high level, the two different approaches in terms of cost.
Autre question? Philippe. Je regarde à gauche, mais c'est à droite.
Thank you very much for the very nice lecture. I was wondering, what is the step which is limiting the efficiency nowadays in this approach? Is this to have the right absorbent, okay, to create exciton with a good efficiency, or is it in the catalytic part?
Yeah. So in this approach, you're always tied to the efficiency of the photovoltaic material. You can't do better than that. So in the amorphous silicon, a drawback is it's only a 7% cell efficiency. The chemistry I'm showing you here with the IV curve called the Tafel slope, that is running at over 80%. So we actually hit almost exactly the efficiency we should, which is 5.6%, because you're going to take the efficiency of the chemistry times the photovoltaic. The way we got to 15% is we used the catalyst with a steeper curve, but the real advantage was the crystalline silicon we used was a 15%. So you'll always be tied to the efficiency of the solar panel. Another thing I like about this approach of a buried junction, if a good photovoltaic material comes along, as new ones come along, it's very modular. You can just slide those in and out along with advances in catalysis. But I will say these catalysts are pretty good as they stand right now, and therefore it's the photovoltaic that limits the overall efficiencies of the system.
Michel Pouchard, on your left.
In many macromolecules in biology containing iron 2+, the spin state changing is very important. In this system, you have iron surrounded by nitrogen atom, and this situation is practically the same as that for the cobalt 3+ with oxygen. Do you believe that these spin evolution between low spin to high spin transition in your materials is playing a very important role?
Yes. So I'll show you where it's playing the most important role, your question of high spin, low spin conversions. And it's, sorry, I'm going all the way back, but it's right here. So the cobalt-2 that's in solution, to get oxidized to cobalt-3 is going from a high spin to low spin conversion. When we look at Marcus theory, this chemistry is 10 to the 5 times 2 slower than the prediction of Marcus theory for exactly the reason you're saying, with this high spin, low spin crossover. And so we've made molecules that molecules that look exactly like our cluster, and we've been able to measure the self-exchange rate to see that. Now, I will say, once you're at the cobalt-3, the chemistry goes to cobalt-4, where we're doing water oxidation. You then drop to cobalt-2, and some of your high-spin material gets there, and the cobalt-2 can get released from the material, but like I said, at the potentials we operate, it gets oxidized and self-heals again. So the high-spin, low-spin problem is intrinsic in this cobalt system right here, mostly for the formation of the catalyst. Once the catalysis is going, we avoid that because we stay in a low-spin state.
Une dernière question. Christian.
So, Dan, thank you for this brilliant talk. One question is related to the discussion you had first with Jean Salençon, that when you use the big electrolyzer, so the indirect case, you need also very sophisticated material for the electrons. And
yes.
Not availability of all platinum and so on. And the second is, so that was a comment, but my second comment is related to the self-healing. Because very often when we think about something which is on the surface and should convert something from a volume, everybody has to come to the surface. So it's enough that one event make a graffiti and destroys the catalyst, then the catalyst cannot do its job.
Right.
And in your case, what I think the superiority is that the catalyst is self-healing. And this is very important because in nature does not care. Just like in the army, you exchange the whole business as a single time. Here you just repair it. So anything that goes wrong is repaired.
Yes.
And I believe this is one of the important things I see in your work.
The self-healing is at the heart of all of this. So let me tell you, because it's self-healing, we can run this out of ocean water. You can run it, we run it out of the Charles River. You could run it out of the Seine, no problem, because it's always fixing itself. And then we're able to use water. If you oxides, when you use oxides, you're generating protons in water oxidation. Proton plus base, the oxide's a basic oxide, you get dissolution, corrosion. So we're able to fix the corrosion, operate in water, and then that allows us, for instance, to interface with biology easily. So the self-healing really is at the heart of this in terms of its simplicity of operation and just coatings. And to go back to that question with the electrolyzer, because I didn't get to all the details, but those things run in concentrated base. There's a tremendous amount of engineering that has to go in to make sure surfaces don't see the concentrated base. That's all eliminated in this process. And the other thing, and we can argue about this, there's one person in the world who loves arguing with me in California. I don't think you need membranes. Membranes are very tough in electrolyzers. But here, hydrogen and oxygen, the solubility of hydrogen and oxygen is less than millimolar. So you can just let them bubble out of solution, and you can literally just go with separators in this design. You don't need membranes. So I see lots of advantages to this type of design that, again, on application, it will depend on how you use it. But I don't know how Michael feels, but I'm basically an anti-membrane person when it comes to hydrogen and oxygen. They're gases. Let them bubble out, and then take the hydrogen and go use it in the dark like photosynthesis does for whatever process you want. And that really reduces cost and complexity when you can get away from membranes.
Thank you very much.
Okay, thank you.